So, welcome, and so in the we will be continuing down with from where we left in the last lecture, and that is on multilayer perceptrons to deep neural networks, and this is where we would be introducing. So, while till the last lecture we had a good amount of briefing and a recap of the learning rules and how to create down this single model and then a single perceptron and then a whole collection of perceptrons in terms of its matrix and the matrix form of representing the data. From there going down to the gradient and what happens with the gradient based learning rule, and then trying to come down to the point of how do we calculate the gradient of the output itself. So, your del w of jw, how it gets broken down into partial products over there, and using these partial derivative products how you can find out the total derivative of the network itself. So, from there we would be entering into the multilayer perceptron model of deep neural networks and how it works out. So, just to do a brief recap of where we left down in the last class. So, that was on the gradient computation part. So, I have 3 scalars x1, x2 and x3, and then I would like to map it down to another predictor scalar which is my p hat, and then how this network was constructed is that I had 3 weights w1, w2 and w3. They were all put into a linear summation block, and there was another added component of what is called as the bias. Now, taking down all of these linear summations over there and the bias together, you get an output called as y, and that is mapped down through a nonlinearity to your predicted output p hat. Now, while we have done the forward pass, which is from x how to get down to p hat, the question which we had raised is how to get down this derivative, and that was by doing a partial product of different derivatives. So, you take the derivative of the cost function, which is derivative of jw with respect to the output which is p, then you take a derivative of p or the predicted output with respect to y, which is the output from the summation block, and you take a derivative of y with respect to w, which is known as the derivative of the linear part of the network. Okay. Now, and how this was, so these were the 3 different parts where we left off in the last class. Now, the point is that this kind of a computation is what holds true for just one single neuron. Okay. And the next point is that if it is not just one single neuron, but you have a collection of neurons or something which is a deep neural network. So, one network, so one bunch of neurons in one layer, then you have another bunch of neurons in another layer, then another bunch of neurons in another layer, typically what you call as a multi-layer perceptron due to its multiple layers form over there. So, that is exactly what we are speaking about. So, I have my bunch of inputs x which connects down to a set of intermediate nodes over there, that connects to another set of intermediate nodes, and that subsequently to another set of intermediate nodes, and finally you get your final predicted output which is your p hat, where each of these intermediate nodes where you are connecting down is what is called as my hidden layer. Now, the point is that we did find out how to get my output from when I just have one single neuron to connect. So, my inputs to my classification neuron and how to get a derivative. The question is that here also you will need to get down the derivative in its own way, but then in order to get this one, you see that clearly there is not just one single connection which connects down my inputs to my output, but it passes through a multiple set of nonlinear transformations along the depth itself, and that is where comes the major question which we have. So, what we do in that case is something tricky. So, let us look into this small part of the network. So, what we do is say that I am looking at one of my particular layer which is say called as the dth layer. Okay. Now, for my dth layer what I will have down is I can write it down in terms of this partial products which is del p of jw, then I can have del y of p which is my output from there. Okay. Now, that can be done as an extended product of del w of yd, which is output which is the linear part of summation which comes down to that particular block. Now, if I go down to my d minus 1th layer, so this is my wd which is just connecting down my output to the dth layer. Now, if I go down to one layer before it, now what we can see is that this del y of del w of yd, okay, so which is the derivative of this linear part of this block with respect to the weights which are connecting these to this blocks over there, can also be written down in terms of a partial product of the output of these blocks, which are z's over here, with respect to the partial derivative of the linear part of this one with respect to the block earlier it. Okay. So, this is my dth layer, the output weights connect down my dth layer to my target output layer over there. This is my d minus 1th layer, and these are the connections which goes down. So, this is my w of d minus 1, and that is where my expansion happens. Now, and similarly I keep on repeating this whole thing together on the chain, and finally what I would get done is on the final part, which is del w of y1, which is my first output layer over there, and that incidentally is equal to whatever is my inputs over here. So, if you just look into your matrix form of representation of y and w's in terms of so y, w and x, which is you just have a linear product of the weight and the x. So, that is a dot product which gives rise to this output over here y. So, obviously my output, my derivative of the linear part of output with respect to my weight is going to give my input to it, which is my x over here. So, this is a typical way in which we calculate down our whole network's gradient over there. So, if I want that my total network has to be solved out, so this is exactly what I would be doing in terms of my calculations. So, you can typically look. So, now that I do not have what is my input coming from here, so what I would be doing is I do not know exactly what values are over here. So, I will be again differentiating this with respect to this, and that is what the chain rule keeps on doing. So, every time you have a del w of y d, so you keep on going to the next previous one. So, over here like this block, that block will again be represented in terms of this dot product of two partial fractions, partial derivative multipliers over there, and these two partial derivative multipliers will again keep on going, and subsequently the final point where it stops is a del w1 of y1, and that is equal to my input, which is x. Okay. So, I believe this part is quite clear to you guys, and quite intuitive actually, not so hard to calculate it out. Now, the next point is that I have my final form of the whole derivative going down something like this. Now that I have this form going down, so my first part of it is what is called as the derivative of my cost function, or known as grad of jw, okay, the gradient of my cost function. The second parts over there is my derivative of the nonlinear transfer function. Okay. Now, the other part is the derivative of the perceptron itself, and which together is what is called as the derivative of the network, and finally is the input to the network, which is my x. Okay. So, these together is what constitutes of any sort of a learning mechanism within a multilayer perceptron or any kind of a deep neural network. So, what you will have to do is you will have to find out what is my derivative of my cost function, you will have to find out the derivative of the network, which together consists of two parts of the derivative. One is derivative of the nonlinear transfer function and derivative of the perceptron together, and you will have to find out what is the. So, this is always known to you because you are just pushing in the input to the network. Now, by solving out this complete derivative over here is what we are able to get down as our neural network learning algorithm in terms of gradient descent, and that is where it goes down. So, that brings us to a very important aspect over here, and which is called as the existential criteria. So, what this essentially means is that in order for the total derivative of the cost function to exist with respect to weight, you need to see that every single fraction of the derivative exists. So, every single part over there we were doing a chain rule of expansion. So, if every single component of the chain rule exists, only in that case you would see that the total derivative of the network as well exists, and you can now learn down it in a perfect way. So, my first component over there, which is del p of jw, is what is called as the derivative of the cost function, and that part should be existing. The let's take down a very simple example, which is let's take down these two cost functions. So, the first one is what is called as the L2 norm, the second one is what is called as the L1 norm, and let us see if its derivative exists. So, I would give you just some moment to ponder on this one and like really contemplate on what do you think, does the derivative exist for each of them. So, what you can do is quite simple. I mean, you can just take a del p of j over here, and then just find out whether the derivative can exist or not. Now interestingly, what will happen is definitely it does exist for the first case, which is a Euclidean norm. So and then that's not so hard to contemplate as well, because I mean, for any kind of an L2 norm, existence of a derivative is a pretty straightforward case. Now you have the second one, okay, and this is where the fun is. So do you think that the derivative of this one will exist as well or not? Just take down a few seconds over here while I just wait. So if you look into this one carefully, the derivative will not exist, okay. And one of the reasons why this will not exist is that you will have some sort of a discontinuity at 0. You see, you have a L1 norm or just a mod, okay. So mod of p minus p hat, this one over there is basically a value which is always a non-zero value, and this does have a discontinuity at x equal to 0, and that is one of the reasons why this direct absolute summation will never have a derivative, okay. Now let's look into the other part of the network, and that is the derivative of the nonlinear so the derivative of the rest part of the network. And now over here, one important point is that the derivative of this nonlinear transfer function, or FNL, that should also be existing, otherwise your del y of p, that will not come into existence, whereas del y of z, that does not have any issues, because that keeps on expanding over and over and over, but your del y of p is something which needs to exist at every single nonlinearity wherever you are putting down. So let's take two different cases of nonlinearities over here. So you see, the first one is a sigmoid function which I have as a nonlinearity. The second one is a 1 by mod z, or this is something like the inverse of the input which goes down to the network itself, but absolute value of the input. And now the question is, does the derivative of each of them exist or not? So let's give you some time. Can you calculate out the derivative of the first function, which is your sigmoid nonlinearity? I'll give you a couple of seconds to just calculate this part. So if you look carefully over here, what you would see is that for the first case, which is my sigmoid nonlinearity, the derivative does exist, and that is a perfectly differentiable function, whereas look into the second part of that again is something which is not differentiable because of the discontinuity at x equal to 0, right. So this are two some like really interesting facts, because like remember in the earlier class, in the first week's lecture, where we were discussing about neural networks and how to make them. So that is where you were exposed to this concept of what is a nonlinear transfer function, as well as like what are the different properties. So one property was definitely to make it bounded in some form, okay. But we also mentioned that there are other properties, and one of those important properties is that the cost function itself, not the cost function, but the transfer function itself needs to be differentiable in its own term. The question was, why do you think it needs to be differentiable, is something which gives you an answer over here, and this is one of the major reasons why you need a transfer function to be differentiable from end to end over there. Until and unless the transfer function is differentiable, the derivative of the complete network cannot exist, and that is the reason why you cannot take transfer functions like say signum of x, because if you take a signum function, that will again have it's like +1 for any value which is greater than 0, and it is -1 for any value which is less than 1, and it becomes sort of 0 in order to be made precise. But the point is, at x equal to 0, you still see a discontinuity coming down into those functions, and that is the reason why these kind of functions cannot be made cannot be used into it, because they are not differentiable and cannot get a total compliance within the way of how a neural network is going to act and make its learning in the reverse way. And that brings us to the point of trying to visualize down our learning rule itself. So now say that I have a multilayer perceptron, and I have my inputs x's which connect down through intermediate weights w1 up to wd, and go down to my final output, which is p hat. And the way of how we are doing down is something of this sort. In the first step, which is called as the forward pass of the network, And this is something similar to what you had done in your laboratory classes in the last week, where you were learning down how to actually learn down a perceptron model and for classification purpose, and we had used a similar kind of a concept over there as well. So, you would do a first would be a forward pass of this x in order to obtain your p hat. Now that you have your forward pass and you have obtained some p hat over there within a particular given epoch, the next point is that I need to compute out my j, which is my cost function. The way of computing this j or the cost function is that I have my output, my predicted output, which is p hat. I have my ground truth of my predictors, which is p, and then I need to find out what is the Euclidean distance, and that was my straightforward way. Now, Euclidean distance for finding out my cost function is not just the only way. We are just sticking down to a very basic form over here, because you have seen that your cost function also needs to be differentiable, and if the cost function is not differentiable, then it does not work. So, we will be going down with more detailed cost functions in a bit later down on this course, where we will be bringing in very specific cost functions which are designed for classification. We will bring in very specific cost functions which are designed for regression problems. So, they would eventually come down, but as of now let us stick down to the very basic form of the Euclidean cost function. So, the next part is that you would be computing whatever is your cost coming down for a given epoch under whatever combination of weights you have. Now, once you find out your cost function, you would be finding out what is the gradient of this cost function, or the del p of jw. That is the first part, which was my nabla of j, or the gradient of j. Now, once I have my gradient of j, the next part is to compute my gradient of the network, or nabla of network, and this gradient of the network is what is the gradient of my p with respect to y's and y's with respect to w. This was my network over there. So, my intermediate points over there for all of these hidden layers where what were giving me some outputs called as z. So, what I was doing is I would in my grad of net is what is my p of y with respect to w, and then that gets again remolded in terms of the output z with respect to p with respect to y's, and eventually this keeps on going down the line. So, once I have this part also computed, and this is very straightforward to compute down by solving out those sets of equations. Now, where comes down the utility of most of the libraries for deep learning is that you do not need to explicitly sit down and calculate these one on pen and paper, or you will not even have to write down a separate bunch of codes in order to design them. If you are using very standard forms of cost functions and very standard forms of nonlinear transfer functions over here, then calculating this and this part, so grad of j and grad of net, is a very straightforward activity to be undertaken now by any of those standard deep neural network libraries. Say the library which we are going to use down in the next class onwards is what is called as PyTorch, and that has very standard ways of doing it. So, over there you would be in standard doing something like this, that you do a forward pass, you get down your output, from there you will be calculating what is your error in terms of cost. From there you find out what is the gradient of the cost. From there you would be next computing out the gradient of the network. Once you have the gradient of the network, then you will be doing an update w, and this update w is something which will happen in the reverse way, as you had seen in these arrows. So, once you invoke update w, then it will be going down updating all the weights from the output side to the input side together. And then next is to continue again with step number 1, which is do a forward pass of x, obtain p, and then repeat all the steps together until and unless you find that your cost function j over there is so this will keep on continuing till your cost function j is above a certain threshold value, which is epsilon. So, the moment you go below this threshold value, so you can empirically set this threshold value. So, this threshold value can be say something like 10 power of minus 3, 10 power of minus 4, 10 power minus 5, or even as small as so it can be larger values as well. So, it can be 1, 2, something of that sort. It all depends on the problem which you are handling, but then so often I do get this question that how do we choose this value of epsilon. Now, that is something which we will be covering down a bit subsequently in the later classes, by coming down to an understanding of the dependence of data to the architecture of the network, to the kind of nonlinear transfer functions you use, and what is the nature of the cost function which you are using over there. So, while certain kind of cost functions they have a like large dynamic range. So, they some kind of cost functions and have a value in the range of say 1 to 10, some of them have a value in the range of 100 to 10,000. Some of them have value which are in order of 10 power minus 3 or 10 power minus 4. So, this epsilon has to be chosen based on what is the nature of the cost function you are using and what is the nature of the nonlinear transfer function you are using. And before that it's like really hard to tell down until unless we enter into that. So, while we would be entering into these very practical experiments, we would be coming down to them one by one and in the lab sessions to understand how these are to be used. Okay. And finally, the end is that once you are below your certain threshold of error, you can just go and stop the whole learning process. Okay. So, what typically happens is that within your learning over there, in while you will be writing down your codes, you would be coming across some very well known terms, and then say net is basically a pointer which is used for defining network. And so, if you look onto the screen over here, you will be getting them out. So, basically net is a variable which defines, it is a pointer to the data structure of how to define this neural network. A net colon forward is basically what executes this part of it, which is to get down your p hat. Okay. Next is a criterion colon forward, which executes whatever is the output of this j. The next part is a criterion colon backward. So, these parameters which go as arguments over here are not indicated over here. So, these are the ones which we will be studying down in the lab classes itself, but it is not so hard to guess down what these parameters would be. So, if I am doing a net colon forward, so what I need is the parameter over here which goes down is just this x over here. Okay. The output of this will be obviously p hat. So, now if I want to do a criterion colon forward, I will have to give down p hat and what is the actual state of p or the ground truth. These two will be the input to the criterion function. Next is when you find out the gradient of the criterion itself or the gradient of cost function, that is what is evaluated using something called as a backward operator. And this backward operator, what it would be needing now is basically the so I know this pointer to this whole thing. So, what it needs is basically whatever is my predicted output and over here. So, what is my cost function. Okay. Now, the next one is the net colon backward, and this is what will be needing this output and this input together. So, it's not so hard to get it done, because if you go back to the earlier slides into the equations, you would see from there how this relates. And now, once this is done, the next part is that you need to update parameters of the network. So, this input over here is this network, the pointer of the network net over here, and these two backward operators or these two gradients which are calculated, and then that together will update down W following the update rules. And this will be updating all of these weights, not just one of the weight. So, each weight, so it goes in a subsequent fashion. For this one updates, then this updates, then this updates, then this updates, and this is what would finish off what is called as one single iteration or one epoch of it. And eventually you can now trace down your error and then either decide to stop or you can continue. So, this brings us almost to the end of trying to understand a deep neural network from a multi-layer perceptron model. And at the end of it, what I would like really suggest you is that you can do much more detailed reading from the textbook on neural networks and learning machines by Simon Haken. And for toolboxes side of it, while for neural networks it is like the most simplest thing which a lot of people get started with is the neural network toolbox within MATLAB, which is for pattern recognition. So, that is the NPR tool. You can alternatively also look into Theano and scikit-learn in Python and Lua for Torch and other aspects. We would be doing down do the labs with PyTorch, which is basically a port of so it's a very recently ported out version of Torch, which can work down with Python environments and makes it much more easier because of the rest of the script availability within Python, and is based on something called as a dynamic graph based architecture, which allows us to compute these forward passes and the gradients much easily in a computationally attractive form. And finally, if you are like really into getting down into more deeper understanding, So the typical suggestion is that these networks don't tend to work down so great on laptops. You might experience heating problems as well. So the best point is that get on a custom workstation. So I mean, a very competitively built up workstation can be achieved with a GTX 1060 or a GTX 1080 and 1080 Ti machines. So this in Indian rupees, this would be costing in less than a bracket of 1 lakh rupees to get a total desktop arranged and set up. You can get down much more professional ones with a Titan X or a Tesla version, or you can even think of buying down any of these. For toolboxes, these are again multiple of these toolboxes, and just for a revision, these are the different reading sources from where you can read down, and these are the two major conferences which where you would see down most of these advancements in the field coming down. So with that, we come to an end on deep neural networks and multilayer perceptrons on the lecturing and theory. In the next class, we will be doing a lab session where you would be going through a code walkthrough and getting to execute it on your side, or as well as on the remote clusters to which you can gain access under certain kind of academic licenses as well. So with that, thanks, and stay tuned for the rest of the classes as well.